Okay, maybe let's get started now. So good morning, everyone. Thanks for joining us for today's SNAPP seminar series. Um, please mute your audio and if possible, unmute your video so that the speaker can see some faces while he's giving his talk. And if you have any questions, please post them on the chat box. I'll keep monitoring them, and then I might interrupt the speaker and ask some of the questions. And also, Richard will take a small 2-minute pause somewhere halfway through the talk to address any other questions. Okay, so today's seminar speaker is Richard Combs. He's an assistant professor from Supelec. He received his engineering degree from Telecom Paris Tech, and he got his master's and PhD in mathematics from University of Paris. He was a visiting scientist at India and postdoc at KTH, and he received Best Paper Awards at Sigmatrix last year and CNSM 2011. His current research interests are machine learning, networks, and probability. Today, he's going to talk about statistically efficient polynomial-time algorithms for combinatorial semi-bandits. The floor is yours, Richard.
All right, so thanks a lot for the introduction, and I'm very happy to be here and to present my work to this audience. Unfortunately, not in person, but I'm sure we'll get to see each other in the coming months or hopefully years at least. So today I will present a recent work on bandits, or it's a subfield of machine learning, and this is a joint work with my student Thibaut Cuvelier and a collaborator from Orange Labs called Eric Gourdin. Okay, and of course, if I happen to catch your interest enough so that you would like to learn more, the paper is available online in the link that I presented. So feel free to have a look. Everything is in there and then some. So okay, let me see. There you go. So first of all, oh yes, I forgot about the most important. My student is soon to graduate and will probably be looking for a postdoc position. So if you like this work and you're interested in working with him, feel free to contact him. All right. So now for the work itself. So let me quickly introduce what is a combinatorial semi-bandit and try to explain why you should care. At least why I care, maybe you should too. So a combinatorial semi-bandit is a bandit problem. So a bandit problem is a problem in which you select decisions. Decisions give you a certain amount of reward, and you do this process repeatedly in order to maximize the total sum of rewards. Okay, so it's most learning problems work like that one way or another. So let me try to present the specifics of combinatorial semi-bandits. So first of all, why is it called combinatorial? It is because the set of actions is a combinatorial set. So a combinatorial set is just a bunch of vectors whose entries are either 0 and 1. So what can this set be? It could be, for instance, a set of paths in a graph. It could be a set of matchings. It could be a set of it could be a basis from a matroid, whatever it is. The point being that our approach is completely generic. Think of any combinatorial set, and typically those sets are large in the sense that the size of the set is much greater than the ambient dimension. Think about, for instance, the number of possible matchings in a graph. That's usually much larger than the dimension of the graph. All right, so the process goes as follows. So it's a sequential process. So at each step of the process, the learner chooses a decision, which is an element from that combinatorial set. Then the environment, which is stochastic, or nature, if you will, draws out a vector of individual rewards, which is called Z of t. So for each I going from 1 to d being the dimension, Zi of t is a Bernoulli variable. Okay, so it means that it's 1 with probability theta I and 0 with probability 1 minus theta I. So think of Zi as the individual reward of item I. And then once nature has chosen Z, the learner observes, so the product between xt and zt. So the product is the product, how do you say this? Forgot the English word. The product of entries, meaning that you get to see the product of x1t times z1t, the product z2 x2t times z2t, and so on and so forth. Is the product of each entry. And the reward is the dot product between x of t and z of t. Okay? And your goal is to find the decision that maximizes the average reward. What is the average reward? Is the expectation of xt multiplied by zt, which is the maximum over x of x transpose theta. Okay? Theta is the vector of means, if you will. So is there a question? I see stuff popping up. No. So the goal is to find the decision that maximizes reward, or in other words, minimize the difference between what you would obtain if you knew the parameters theta in advance, my bad, and the cumulative reward that is actually obtained by the learner. It's basically the difference in terms of cumulative reward between you, this is you, and an oracle that knows the latent parameters in advance, an oracle that knows everything and plays optimally. So this applies to a large variety of things. So for instance, if you are networking guys, you can understand this as an example of route. So here, the combinatorial set would be a set of paths between a given source and a given destination. Zi of t would be the reward obtained on one edge. And then what you're trying to minimize or maximize is the sum over all the chosen edges of the rewards. And the rewards could be something like minus the delay or whatever. Okay, same thing for resource allocation. There, the combinatorial set would be, for instance, a set of matchings between, let's say, users and resources, and so on and so forth. So my point being that this problem can be applied to a wide variety of control problems and network problems in which you have uncertainty. All right, so now I said that I wanted to speak about polynomial time algorithms and statistically efficient algorithms. So I need to give you some algorithms. So I'm not the first to look at this problem. And let me present the basic algorithm in order for you to understand what's going on in here. So let us define ni of t, which is simply the number of times from 1 to t minus 1 that we have observed item I. So when xi of t equals 1, it means that we select item I and we get a sample from theta I. If xi of t equals 0, then we do not select I and we do not observe anything. So ni of t is simply the number of observations that I can use to estimate theta I, and then theta hat I is just the empirical reward obtained when I choose item I. It is how should I put this? The most natural estimate of the unknown parameter theta I. So of course, I wish to know theta I because I want to find the decision that maximizes the dot product between theta and x. Okay. So now what are the reasonable algorithms? So most of those algorithms fall within a class which is known as using optimism in the face of uncertainty. So to understand this, look at the simplest one, which is called CUCB. So C stands for combinatorial, and UCB stands for upper confidence bound. The name is obvious when you look at the formula. So this algorithm says that you should choose the decision at any time that maximizes the dot product between x and the empirical reward, and a sum over I of square root of xi logarithm of t divided by ni of t. So what is the rationale? The rationale is very simple. I want to find the x that maximizes the dot product between theta and x. However, I do not know theta. So what can I do? I could simply find the x that maximizes the dot product between an estimate of theta and x. So the problem of this is that if you have not sampled the decisions enough, you are going to miss the optimal decision. Okay, you're going to play, as we say, greedily. Means that if you do not estimate theta correctly, the one that maximizes this part of the expression is not necessarily the optimal decision. However, if I account for the uncertainty by giving each item a bonus, this can be understood as a bonus, which is proportional to the standard deviation of the estimate. So if I have ni of t samples, the standard deviation is proportional to 1 over square root of ni. Okay, so this should be understood as a standard deviation. Then you get CUCB. So it's called an optimistic algorithm because this expression with a high probability is larger than theta transpose t. So we are being optimistic. This is the largest value that decision x can have if we saw some very bad fluctuations in theta hat. Okay. So if some of you are familiar with UCB, this is the extension of UCB to combinatorial bandits. Okay, so this algorithm is fine, but there is a better algorithm that has a smaller regret. It's called ESCB. So it's an algorithm that I propose with a bunch of co-authors, in which we do pretty much the same, except that instead of adding the standard deviations, we add the variances and then we take a square root. So once again, if you're a statistics guy, the reason why we do this should be obvious to you. It is because this expression is very conservative. Okay, if you have if you take a sum of random variables, the standard deviation of the sum is not the sum of the standard deviations if they're independent. What's going to happen is that the variance of the sum is going to be equal to the sum of the variance. So by going from here to here, what we take into account is the independence between each item. Okay. And so those are two of the well-known, let's say, upper confidence bound algorithms. And there's another kind of algorithms which is known as Thompson sampling, or it's called a sampling algorithm. So here the idea is that, okay, I realized that I made an error in the formula. So here, the formula should not be theta hat t transpose v of t. It should be x transpose v of t. So the idea is once again quite simple. Say that I want to find the optimum of the optimum of theta transpose x. Now, in order to account for the uncertainty in the estimation of theta, what I can do is replace theta by a sample from its posterior distribution. That's a Bayesian approach. Okay, and this Bayesian approach surprisingly works, and it works very well actually. So in short, you take this expression and you replace the estimate theta hat by a sample from its posterior distribution, and you get Thompson sampling. All right. So now this is where things get interesting. Roughly, the picture looks as follows, and you will very soon understand why we talk about complexity in the title. Okay, so the summary of the situation is here. So define M, which is simply the size of the largest decision. So this is the sum over I of xi, and if you maximize this over x, you get the size of you get the maximal size of a decision. And most important parameter is called delta min. So what is delta min? It is simply the gap in terms of reward between the best decision and the second best decision. If you're remotely familiar with bandits, this is the parameter that appears everywhere in the regret. The regret is usually inversely proportional to this gap. So the problems with a small gap are usually very hard. Problems with a large gap are usually very easy. Why so? Simply because it's difficult to distinguish the best decision from the second best decision if they are very close to each other in terms of reward. Okay, I think that makes a lot of sense. So the picture looks as follows. So if you look at CUCB, it has a regret which is proportional to dm logarithm of t divided by delta min. Okay. So this is not optimal. The regret of Thompson sampling is the same. dm multiplied by logarithm of t divided by delta min. ESCB has a much smaller regret. Why so? Because the factor m in the previous expression is replaced by a logarithm of m squared. So usually m is much larger than logarithm of m squared. All right. So going from here to here, going from, let's say, CUCB to ESCB gives you a very substantial reduction in the regret. And even there exists a regret lower bound that says that the regret of any algorithm must be at least greater than d multiplied by logarithm of t divided by delta min. So in short, here we are a logarithmic factor away from the optimal. Okay, so now you must be saying, well, let's use ESCB and go on with our lives. Well, it's not that simple, because the problem is that CUCB and Thompson sampling do not have the best regret guarantees. However, their complexity is polynomial in the dimension. So this is fundamental when you're dealing with large problems, let's say matching a large number of resources or finding paths in a large graph, because if anything, if the computation time required to output a decision does not scale polynomially in the dimension, you'll never be able to apply your algorithm. It will have great regret guarantees. It will have a very good statistical efficiency. However, its computational efficiency will be terrible. And of course, we want to apply our algorithms to the real world, or at least I would like to. And the problem is that ESCB, let's say provably, has a complexity which is linear with the set of decisions, the size of the set of decisions. So if this set is small, it's all well and good. But typically, the size of the decision set is exponential in the dimension. Think, for instance, about the number of matchings in a complete bipartite graph. This is a very big number. It's factorial in the dimension even. So our contribution is to show, I mean, my basic question when undertaking this research was to say, okay, is it possible to be statistically efficient and computationally efficient? Or is there a trade-off between this and that? So the answer is fortunately or unfortunately no, in the sense that there exists an algorithm that has the same regret guarantees as ESCB. So that is a small logarithmic factor away from the lower bound, and that has a complexity which is polynomial in the dimension. So there is no trade-off between statistical efficiency and computational complexity in combinatorial bandit. This is the outcome of what we did. All right, so let me just give some examples, and then I will take a small pause in order to take questions, if any. All right, so a lot of what we do has to do with the combinatorial structure of the set. Okay, it's very important, and I think our work is as much combinatorial optimization as it is, let's say, machine learning or bandit or whatever you may call it. Okay. So here are a bunch of examples of combinatorial sets that are of interest to us and for which our approach actually applies. So the first one is well known, is called the set of M sets. Or it also is what happens when the decision that you take is to select M items out of D. So people do this, for instance, when they do things like ad optimization. They have M places and they have D, which is very large number of ads, and they want to find the ads that maximize the sum of the click-through rate, let's say. Okay. Then you have spanning trees. So once again, I think you understand what is a spanning tree, and you understand why we would like to find, for instance, a minimum weight spanning tree in a graph. So think about any sort of networking application in which we want to connect entities with each other using a spanning tree. Okay, hope that makes sense. More generally, those two things are example of elements of a matroid. Okay, so our approach also works for matroids. So for instance, well, you can think of any matroid you want, for instance, a set of spanning trees, but not limited to that. So usually these three kind of sets, so M sets, spanning trees, and matroids, are considered somehow easy, between quotation marks. So because they are of the, let's say, matroid family. However, there are some sets that are usually harder and for which no and for which things get a bit more, let's say, hairy. So let me be more specific. So you can consider the set of ST paths. So it's the set of paths in a given directed acyclic graph between one source U and one destination V. So in fact, this was our initial motivation because my student was interested in routing. So we wanted to solve this problem for routing, but it turns out that we can do it for other sets as well. Then you have the set of matchings. So once again, matchings in a bipartite graph. So you do this whenever you have to match, for instance, whenever you have to match resources and users, or it could be that you want to. So I think when you do routing in a switch, you also have the same sort of phenomenon. You're looking at matchings. Knapsack sets. So I think everyone is familiar with the knapsack problem. So the problem is to optimize a linear function under one linear constraint. It's actually a very hard problem. So here we consider a more general case when you have several constraints. However, there are not too many constraints. So in the sense that the size of A, the size of A should be, let's say, fixed 1, 2, 3, 4. It should not scale with the dimension. If it scales with the dimension, then we can't do things in polynomial time, or at least I don't know how to do it. But even for this type of set, we can do something. And finally, matroid intersection. So matroid intersection is an example, is something that covers matching. So matchings in a bipartite graph are an instance of matroid intersection. Okay, so all the sets for which our approach actually applies and for which we can provide low complexity, low regret algorithms. All right, so maybe I will stop here. So I haven't presented much results yet, but maybe to take a few questions or to clarify.
So can I ask a question if nobody else has questions? So how much a difference does it make when you observe, like for example, when you choose your action represented by X, you observe each component, like the reward from each component where X sub I is equal to 1, right? So how much a difference does it make if the thing you observe is the inner product, the total reward you get from your action?
Well, it's much harder because then what you have to do is compute some sort of to do some sort of, let's say, linear regression. So it's strictly harder than semi-bandits. So what you're alluding to is known as the full bandit or the bandit feedback.
Okay, so that's where the semi-bandit comes from. I see.
Yes. The semi is actually because full bandit means what you just said. But yeah, for instance, when you do routing, if you get link per link feedback, that's semi-bandit. If you get how do you call this, end-to-end delay, then that's full bandit. So
I see. Okay. Yeah.
Does that make sense?
Yeah, makes sense. Thanks.
All right. So now I will. This is my last. My last slide in which I have to introduce stuff before I can actually present the results. So what is in fact very important in this problem is whether or not it is possible to solve certain optimization problems over the set of decisions, over the combinatorial set. So the first one is linear maximization. Okay. So typically, if we can do linear maximization over this set, then, I mean, if you cannot do linear maximization over this set, things are going to get complicated. So think, for instance, if X is a set of independent set of a graph, computing this is typically very difficult. In fact, it's NP complete. So Why am I saying that if this doesn't work, then we're in a difficult situation? Is because even if I gave you theta, even if you were the oracle, you wouldn't be able to find the optimal decision. So this sounds like a hopeless endeavor. So now there is another problem which is strictly harder than this, what that I call index maximization. So here the goal is to maximize A transpose X plus B plus the square root of B transpose X over the combinatorial set. So this problem, on the other hand, P2, is typically very hard. And it is in fact in certain cases NP hard. Okay. So why is it that this problem is important? It is because ESCB involves solving that problem. In fact, the decision chosen by ESCB is precisely the solution to this problem with a well-chosen set of entries. All right. So now the third problem that will be instrumental to our work is what I call budgeted linear maximization. So what is budgeted linear maximization? It means that you would like to maximize a linear function over the set of decisions subject to a budget constraint, meaning that A transpose of X should be greater than S. So I know that typically people call budget a budget constraint when something, when a linear function of X must be smaller than something, but whatever. Let's say it's a reverse budget constraint, whatever. Okay, so in fact, a lot of our work is based on studying that problem. So I think if I show the algorithm, then you are going to understand. So our approach, the way that we solve the problem, is to say that so ESCB is a good algorithm. However, it is not implementable in polynomial time, and it's provably impossible because that would involve solving some sort of NP-hard problem at each step. So it is dubious. On the other hand, what we said is that what if we replaced the maximization of the index? So this expression here is the quantity that is maximized by ESCB by an approximation of it. Or in other words, since we are unable to solve this optimization problem exactly, so be it. Let us attempt to solve it in an approximate manner. So where are the approximation factors? So we want to find a decision X of t such that the optimal solution of this is greater than delta of t, which will be a small additive error, plus theta hat t transpose X of t. So this is just the same thing as this. And here, instead of having 1 in front of the square root, we are going to have 1 over epsilon of t, where epsilon of t is once again a multiplicative approximation factor. Okay, so if this expression looks bizarre to you, just look at the case in which delta of t equals 0 and epsilon of t equals 1. Then the only x of t that will satisfy this expression is simply the argmax, the argmax of this expression. Okay, so in simple terms, we are simply looking for an approximate version of ESCB. Hence the name AESCB. A stands for approximation. So of course, I mean, anyone could have done this. It's somehow obvious. The real question is, how do you find this xt? Is it even possible? So I claim that yes, and I claim that I can do that in polynomial time. So let's do it. No, let's not do it. Let's look at the regret of AESCB first. So there's a lot of math written on the slide, but what I would like you to focus on is the second line, the expression that is here. This is more or less the takeaway message, is that if you select the parameter epsilon of t to be a constant, whatever that is, it can be 1 over 2 or 1 over 4 or 1 over 8, let's say 1 over some arbitrary universal constant. And if you let delta of t, which is the additive error parameter, vanish at any arbitrary rate, you can let it vanish as 1 over, let's say, logarithm of t, 1 over log of t, who cares? Then the asymptotically, the regret of AESCB is the same as the regret of ESCB. So in short, if we have a constant factor epsilon and a factor delta that vanishes, we get exactly the same regret as for ESCB. And I recall ESCB is not implementable in polynomial time. And I claim that ESCB with those parameters is indeed implementable in polynomial time. So above you have a complete, let's say, finite time regret bound that holds for any value of t, which is it's a bit more complex. So I'm not going to go over it too much. The important term is here. It is the asymptotic term. And another interesting fact is that if it is possible for you to select delta of t to be equal to a constant as long as you know the gap between the first and the best decision and the second best decision. So in general, if you do not know this gap, if you have no information, let's say, you can simply select epsilon and delta in this fashion and everything is going to be fine. But if you have some additional information that comes from a model or the environment, whatever, then you actually get a regret bound of this form, and you do not even need to let delta t vanish. So it's even better, because when delta is small, there is more. Let's say the computational complexity is higher. So if you know the gap, you get this. If you do not know, you get the same asymptotic regret as ESCB. Okay. So this is let's say the statistical part, the regret part, if you will. But now we need to look at the complexity. Is how do I actually find such an xt? So the answer is both simpler and more complicated than what you are thinking. So the simpler part looks like this. So you should remember what I said about optimization over the set of decisions. I said that I am interested in budgeted maximization. So let's go back to my slide here. Okay. So in fact, what you can do is something very easy. Look at this expression. I'm trying to find a maximum. I'm trying to maximize this function here. So what I can do is decompose the expression according to the value of sigma square transpose t multiplied by x. What I can say is that, for instance, let's say that this has 10 possible values. Then for each of the possible values of this expression, I maximize this expression subject to the constraint that this should be equal to a given value. Okay? I simply decompose this expression according to the value of this. So this is the idea, and in details, it works pretty much like that. So what you should do is to select a factor psi of t, which is a discretization parameter, which is a rounding parameter. So what we do is that we scale and we round the empirical reward from each item using psi of t. So remember that theta hat is between 0 and 1. So AI is an integer between 1 and psi of t. So psi of t is indeed let's say discretization or scaling that we use, and bi of t is just epsilon, is just psi square multiplied by sigma square. So then the next thing that I'm going to do is to use those two guys as an input to my budgeted linear maximization. Okay, basically I want to fix the value of this guy and maximize this expression. So this is precisely what I do. So if I can compute an epsilon optimal solution to the budgeted linear maximization problem over X, this is what it is. And then I optimize over the possible values for the budget. So essentially, I'm optimizing over all of the possible values of sigma transpose t. Then I get a decision which satisfies my criterion. So once again, if this math troubles you, just think about the simple idea that whenever you have an expression that is a sum of two things, you can always fix the value of the second thing and optimize over the first thing. Really, it's that simple. Okay. So so once again, this is very generic and very, let's say, banal. But the cornerstone of the analysis is that I can show, and this is what we have done, that budgeted linear maximization is feasible in polynomial time for all of the structures that we have listed. Okay. So performing all of this takes an amount of time which is polynomial. Okay. The possible number values of S here will be polynomial, psi is polynomial, and solving any of those problems takes a polynomial amount of time. So all of that stuff gives you a polynomial computation time. So of course, in order to close the loop, I need to show you actually how you do it. So I'm not going to show you because it's too complicated. I mean, let's say it would be too long to explain all of this in the time that I have. So here, this just says that if you use this approach, you get pretty much the AESCB algorithm in polynomial time by solving a polynomial number of optimization problems that are budgeted linear maximizations. Okay, and I claim that indeed P3 can be solved in polynomial time because for all of the structures that I have given, I can actually do that. So let me try just to go through some of the structures and explain to you how you can do budgeted linear maximization. So as I said, it is very non-trivial to do budgeted maximization over those structures, and we go in full details on how to do it in the paper. So once again, please check out the paper if you want to know the lovely details behind this picture. And I'm also mentioning that delta of t once again can be chosen as any function that vanishes. Why is this important? It is because the amount of optimization problems that we have to solve depends linearly on psi, and psi depends in an inverse fashion on delta. So in other words, if I divide delta by 2, psi gets multiplied by 2, and doing all of this takes twice as much time. So I would be happy not to have delta to be too small. And what I said is that you can take delta equals 1 over log of t, or delta equals 1 over log of t, whatever. Any function that vanishes, you're going to get the same asymptotic regret. So this is nice. So now, how do you actually do budgeted linear maximization over all of those sets? So for the M sets, you can do this using dynamic programming. You can do it using dynamic programming by saying, okay, you take an item I and you say, if I take item I, then I have to do solve basically the same amount of problem, except that M is replaced by M minus 1 and the budget is replaced by another budget, etc. So using dynamic programming, you can actually do this in polynomial time. So in times dm times a factor that depends on delta. For spanning trees and for metroids, it is in fact the same thing in the sense that there is a generic algorithm that works for all metroids. And here, we do not know how to do budgeted linear maximization exactly. However, we have polynomial time algorithms. We have polynomial time algorithms that work with a factor of epsilon 1 over 2. So in short, you get a solution which is at least 50% as good as the best solution. And this is good for us because as long as epsilon is a constant for us, we get the same asymptotic regret. So this is great. So basically, the algorithm is a bit complicated, but the idea is basically to use relaxation. So instead of maximizing a function over the set of spanning trees, we maximize the function over the convex hull of the set of spanning trees. So that usually does not give you an integer solution, and then there is a clever way of rounding the solution. So it's a bit complex once again, so I do not want to go into the details, but it looks something like an approach proposed by Guémence in the 90s, I think. So once again, check out the paper. So for the paths, for ST paths, which was our initial interest for routing, we can do this using doing dynamic programming, sorry. So once again, how does that work? We say that if we want to go from let's say U to V, in order to go from U to V, we should go from U to W when W is a successor of U, and then from W to V. So by solving the problem for all sets of let's say for all possible sources, we essentially can compute the solution by dynamic programming, and in a time which is let's say almost linear in the dimension. So this is very good. And for the set of matchings and for metroid intersection, it works the same. We cannot compute the budgeted linear maximization exactly. I believe it's an NP-Howe problem. However, we can get an approximation ratio of 1/2, which is just as well for our purpose. And once again, the approach looks a bit like that of the spanning tree. So first you do a linear relaxation. So that gives you something that belongs to the, instead of having a matching, you get a point on the convex hull of the set of matching. So it's also called the Birkhoff polytope if you want to impress your friends at the dinner party. Or it's also the set of doubly stochastic matrices, whatever. And then we have a clever way of rounding the solution, or let's say starting with a set of solutions, refining them, and iteratively converging to, let's say, a matching. So the complexity is quite high, but at least it's polynomial. So if you're a computer scientist, you say that it's quick because it's polynomial, right? Well, anyway, so I'm not sure that this is optimal, but at least it's polynomial. See, I feel like it's a step in the right direction, and maybe there are faster approaches, whatever. I'd be interested to know. All right, so thank you so much for your attention, and thank you for attending the talk. So the takeaway message is that AESCB, or the proposed algorithm, is, as far as we understand, the first algorithm that is implementable in polynomial time, and that is statistically efficient, or at least as statistically efficient as the best algorithms. So the question on whether or not you can get polynomial time and let's say regret optimality is still open to a certain degree. This is beyond what we have done anyway. So there is much more in the paper. So there is pseudocode for all of the routings that I've described. So for instance, we described in details how to do a budgeted linear maximization over all of the combinatorial structures that we have listed. We have, of course, numerical experiments, proofs. Something which is a bit more unusual is reflections on how to use commercial solvers, because if you're familiar with combinatorial optimization, I mean, I'm not very familiar with combinatorial optimization, but my student is very familiar with it. And a lot of their work amounts to essentially finding a good way of inputting the problem into a solver. And we've done some experiments. This enables very large acceleration. So it's something to consider. And finally, we have made all of the code to be freely available on GitHub. So the reference is in the paper on archive. So you can actually try AESCB on all of those combinatorial structures, and all of the code is inside. So all of the budgeted linear maximization, etc., all of that stuff. And of course, more shameless advertising. As I said, my student will be looking for a postdoc very soon. So if you're interested in working with him, then contact him, or contact me, and I will connect the both of you. All right. So that concludes my talk. Thank you so much for your attention, and hopefully we can answer some questions.
Let's thank Richard. Maybe I'll start with a question. Richard, can you tell a little more about the budget constraint, how you solve the budget constraint problem for the matching problem?
Okay, so let me go back to, okay, this would make things a bit simpler. All right, so as I said, the basic idea is to do relaxation. Okay. So what I'm going to do is that I'm going to take advantage of the fact that maximizing a linear function over the set of matchings is very easy.
Right.
Why so? I mean, it's of course well known if you've taken a combinatorial optimization class, and the way that we do this is using, for instance, the Hungarian algorithm. Classic, it's quite classic. So now what I can do that is instead of maximizing B transpose X, I can do relaxation, which is I'm going to maximize B transpose X plus lambda multiplied by A transpose X minus S. So this is the Lagrangian approach. All right. So now, so now, if this was a continuous problem, things would be over. I would just have to search over all of the possible lambda in order to find a solution. However, we are doing combinatorial optimization, so nothing is ever nice. And if you inspect the solutions of this optimization problem as a function of lambda, what you can find is usually two solutions. One solution that is feasible but suboptimal, and another solution which is infeasible but better than the optimal in terms of the objective. So now you get basically two matchings, and the question is, how do we merge them? So for instance, if you take let's say the one that has the largest function value, you become infeasible. If you take the one that has the smallest function value, you're not guaranteed to be optimal. So the way that you can do this is basically by exchanging items between the two of them. So it's a bit complicated. You take the two decisions, and then you take the symmetric difference between one and the other. So the symmetric difference would be a set of paths and of cycles. And then if you detect a cycle, you can attribute it to one or the other, and then you do that again and again and again. So
I see.
So yeah, you can look at the full details in the paper, but that's roughly the idea.
Okay, thanks. Are there any other questions?
Okay, I'll ask a question. I'm Yash. Thank you for the talk. It was very interesting. So I was wondering, can you give us some lay of the land in terms of what are the big open problems in this area?
Yeah, so that's this would be a personal opinion once again. So well, to me, what's interesting is for instance, is can we do better than just have can we do something better than have just polynomial complexity? Okay, is it possible to do things, let's say, with d to the 2 or d to the 3? Because I mean, if you have a polynomial of large dimension, it is still quite impractical. So another interesting question to me is so if you're not familiar with the field, there is something that I omitted here, is that there exists actually an algorithm which is which attains the regret lower bound. Okay, so it's called I forgot the name, ESSB, I think, or OSSB, sorry. So it's you can look on my webpage. It's basically an algorithm which is generic for all let's say structured bandit problems. The question is it possible to implement this algorithm in polynomial time, for instance? I think that's a difficult question, but it would be interesting still. And yeah, more generally, let's say that I give you a regret bound of a certain order. Can you tell me how much computational complexity is required? Something like that. I mean, to me, what I find interesting in these problems is the trade-off between computation and regret, let's say. I hope that answers some of the questions.
Yeah, thank you.
Yep.
If there are no other questions, let's thank Richard again.
Thank you.
So we'll meet again next week at the same time, and our speaker will be Anna Busik from India, Paris.
All right. Bye-bye.
Bye.